Hello, this is our final concept selection presentation. We are Group 22, the River Water Pump Team. My name is Einar Sterling.
I'm James DeMayo.
I'm Xander Kelmer.
I'm Garrett Schweitzer.
And I'm Luis Vargas.
So our problem statement that we selected was how to generate water from a water source. Reason why this is a problem is, as seen here, one article from UNICEF and another one from Life Water, as shown here. 1 in 4 people lack safely managed drinking water, and 3 in 10 people during the COVID crisis couldn't even wash their hands because they had limited access to water. Now, that's just not just as far as safety goes. That comes into play when people have to gather water. So according to the World Health Organization, it should take a person about 30 minutes to travel round trip to collect necessary water for the day. So as you can see here in this photograph here, to have access to a water source like this, there's several hazards in the surrounding landscape due to elevation and also the water flow from this river shown here. There's in areas that are underdeveloped, they don't have access to electricity and the facilities to allow for water transportation like seen here in the States. So that could be a very critical problem in those areas. So the goal that we were set was to deliver water at a height of 5 meters to generate a volumetric flow rate of 1 gallon per minute, and to be able to accomplish these tasks without an external electrical source. So here we've highlighted some of the customer requirements and their associated engineering characteristics. We've obviously have on this list what I just presented to you earlier, but we also found some hidden customer requirements, such as having a high reliability and high lifetime for the device that we're trying to create, and also to have low maintenance and low ecological impact. Some of the constraints that we'll have for this device obviously will be weight and size, the material that we're going to be using. Terrain will also be a huge one, and also cost and complexity. And again, river flow rate will also come into play with that as well. For product functions, we have listed as creating a support system, collecting water, and then generating pressure to elevate the water that we've collected. And the decision criteria that we've found were cost, volumetric flow rate, material elevation limit, lifetime, and environmental impact. All right, so from here, we'll be going into concept generation and selection. I'll turn it over to Xander.
So for our concept generation, our development process for that is we took our CRs and ECs as previously mentioned. We have product functions based off of those. And then we brainstormed a bunch of different design concepts for those product functions. And then we utilized methods like the analytical hierarchy process and pew charts to help rank and choose which of those concepts were the best for each product function. And then after that, we assembled together our preliminary design for our product. So here are the pew charts. So for our first product function, we have water collection, and our 4 different concepts are the water wheel scoop, a fixed funnel, a bucket, and a standard hose to act as an inlet. And using the water wheel as our datum, the fixed funnel turned out to have an advantage in each of these categories, all these decision criteria. Our second Our second product function that we investigated was pressure generation. For that, we have the spiraled hoses datum, and then we have an electric pump, a ram type system, and a rotating cylinder with a check valve. So the spiraled hose design ended up being the best. And then for our support system, we have the concept of floating design with anchors, telescoping pilings, fixed pilings, and then also a suspended product. And for our for that, they were all pretty even, but the telescoping pilings and the suspended design ended up being the best. So next, there's a summary of our top concepts. So for water collection, while the fixed funnel seemed to be the best solution because of its simplicity and functionality, we ended up not going with this concept because it was incompatible with our pressure generation concept, which was deemed more important to the product design as a whole. So for the spiral hose design, it is very beneficial because it works well with the constant motion of the river, and it's fairly straightforward as a design. And for the support system, telescoping pilings and the suspended system were each shown to be a little bit better, or the best concepts. But we're not deciding to go with this preliminarily as our design, because they may be more difficult to prototype. So we may start with the floating support.
So for our analytical hierarchy process, we use this so we could better understand our design criteria and consider how they relate to one another. So here are some results that we came up with. So for elevation limit and volumetric flow rate, we found at about 25%, which makes them by far the most important. This is because they're both critical to meeting the requirements of our problem statement. Lifetime and cost were both around 15%. This is because lifetime and cost are just the most important non-required design criteria. Target audience we have is not going to be easily able to replace or repair this system just because of financial or geographical limitations. We can go into this on the next slide. So here we have, in order of importance, the design criteria fleshed out. So our elevation limit and volumetric flow rate, we need to meet the requirements to have pumping water 5 meters at 1 gallon per minute, and we have to meet this above all else, so it is the most important. Lifetime and costs, lifetime, rural customers cannot easily get replacement parts or replacement systems if they have any failures. And for cost, most people will not have the money to replace parts, and we can't have people suffering breakdowns on systems like this that could be critical. The next most important are system size, weight, component count, and installation time. So these all relate to size, portability, and ease of installation and maintenance. The system should be intuitive and physically simple to install and maintain because we have people of all different backgrounds operating it, and we can't assume that any customer is going to be especially skilled in any background with assembly or repair work. And the last most important DC is our environmental impact. This is least important on our list, but it's certainly not unimportant because we need to minimize disturbances to the environment because this can have wider impacts on our users and other users of the waterway. So our parts need to be non-toxic and the system needs to be unintrusive for wildlife and people alike.
For our considerations, we started out with the social considerations of the product, a low cost and ease of implementation is going to be a requirement for impoverished communities or droughted communities that would provide the greatest benefit. This is necessary because it provides not only a vital amenity, but according to worldvision.org, it is statistically proven that access to water in impoverished communities not only increases the percentage of those able to go to school, but also to actively work in their communities.
For our environmental considerations, we are focusing on minimizing disruptions to plant and animals. and we're making sure that it will not pollute the pumped water and the river.
For physical considerations, we need the installation of the pump to be as simple as possible for all different types of users, and the pump has to be light and compact enough for anyone to move and assemble on site where it's needed, because that site isn't guaranteed to be easily accessible. For cognitive considerations, the pump should be simple to assemble and maintain, because once again we have people of various backgrounds working with it, and the number of components should be kept minimal to ensure that assembly is intuitive and that people without mechanical experience can handle setting up the system.
For our final concept, we decided to go with the ballast spiral approach for the secondary pressure generation system. A small water wheel designed to be small enough to be wieldable and easy to install, with the ultimate intention of also being modular for expanded capacity. Floats on ballasts and rotates due to the flow of the river, scooping water into a hose, which then travels to a main line and then into an air chamber secondary pressure system. For our critical functions, we have collect, and this happens by, as the wheel rotates, scoops with small debris filters funnel water into the hose. The water is then pressurized by the motion of the wheel and spiral hoses, where water is then forced into the main pipe/axle. That water is then emptied into the air pressure chamber, where compressed air is leveraged to generate more pressure to force water up a smaller outlet hose. For our supports, we have ballasts, as mentioned before, that will be anchored to the bottom of the river by a tie, and these passively channel water into the paddle area. And we also consider delivery of the water as a simple outlet hose leading up to the 5 meters we needed.
For our convincing evidence, you all might be wondering, how do we know if this design is going to work? Well, round pumps, wind power systems, and spiral pumps have been the most used systems around the world. These type of systems have proved to be efficient and easy to build. Many manufactured working designs around the world exist with good outcomes. For example, Akista. Akista specializes in designing different types of spiral wheel systems. As we can observe in the charts to the right, some of their tested data is shown, and it gives us an idea of what our results could look like. As observed, they can pump water up to 20 meters in height and about 2 kilometers in distance, which is more than what we're required to achieve in this project. As an addition to the Akista design, many patents around the world are always trying to optimize and improve the spiral wheel. A list of our advantages and disadvantages of the system are shown. Our most important advantages are that the system is cost efficient, materials are easy to find and obtain, and that it is resistant to moderate weather and changing river height. Making the system affordable with materials that are easy to find is going to let communities with lower income and resources to build the spiral wheel. Also, making it resistant to moderate weather and changing river height will allow the user to keep getting water in different type of scenarios. The most influential disadvantages are the river height and the flow rate. As we observed on the previous slide, the system requires a certain depth so it can fit in the river, and a certain flow rate so it has enough power to rotate. Thank you for your attention throughout the presentation. If you have any questions or suggestions regarding our project, please feel free to contact us. Now we will proceed to our task tracking and citations.